Hello, I'm Bolun. I'm currently working in cost, but this work is done when I was in Beihang University and NYU with Zachary, Ferguson, Jiang, Marco Attene, Daniele Panozzo, and Teseo Schneider. They are from NYU, MIT, and University of Victoria. I'm here to present our recent work, fast and exact root parity for continuous collision detection. Continuous collision detection, CCD for short, is widely used in physical simulations. It's an important tool to guarantee two moving objects will not pass through each other. CCD algorithms report positives when collision happens, otherwise report negatives. To simplify the problem, people usually use two steps of linearization. First, angle meshes are used to represent the models. Second, assume the vertices of the triangles move along linear trajectories within a time step. After the linearization steps, the CCD between two objects can be converted to iteratively detecting collisions between two of the triangles. It can be obtained by two subproblems: vertex triangle CCD or edge-edge CCD. It means that if a point hits a triangle, or any two edges hit each other, then the two meshes have collisions. Let's take edge-edge collisions as an example to show how to formalize this problem. The four vertices E0, E1, E2, and E3 move along linear trajectories from start positions when time equals 0 to their end positions when time equals 1. We can derive the parametric functions of the positions of the four points ei at time t by using linear interpolation of the start points and the end points. Then we parameterize the two edges with u and v. Any point A on the purple edge can be represented by a parametric function with parameter u, which linearly interpolates E0t and E1t. And similarly, we can represent a point B on the gray edge using a function with parameter v. It's clear to see that if there exists UVT which satisfy that A equals B, then collision happens. Then we can derive the CCD formulation as a map from R3 to R3, which equals A minus B. And collision happens if and only if there exists UVT that FEE equals 0, 0, 0, which is the origin point of the Cartesian coordinate system. And similarly, we can get the vertex triangle CCD formulation. Many methods attempt to exactly detect collisions by solving these functions under floating point arithmetic. But unfortunately, none succeeds. This page shows the statistics from our previous work. It shows that these methods are either too slow or report too many false positives, or have false negatives, which means missing collisions. Among these methods, Brucho et al. Propose a geometric method to detect the root parity of CCD functions. Let's still take edge-edge collision as an example to explain this algorithm. As mentioned before, finding collisions between two edges equals to find the roots of a low-degree polynomial. And Boutroux et al. Noticed that it maps a unit cube to a generalized hexahedron. Checking if collisions happen can be done by checking if the origin is contained in the hexahedron. However, this is not an easy task. Since the mapping is nonlinear, it may contain multiple roots, and FEE maps the boundary of the domain as bilinear surfaces, which makes the shape of the hexahedron complicated. Intuitively, if the codomain is a closed, continuous shape which contains the origin, then we can cast a ray from the origin. The ray will have an odd number of intersections with the boundary of the shape. In this case, the number of intersections is 3, which is an odd number. And in this case, there's one intersection, which is also an odd number. If the origin is not inside, then there will be an even number of intersections between the ray and the boundary. In this case, there are 2 intersections. If we cast another ray, we may get 0 intersections, which is also an even number. However, this method may fail when the codomain folds itself and cause 2 roots. But the parity of the intersections can still be used to indicate the parity of the roots. It's called the root parity lemma. It means the parity of the number of intersections is the same as the parity of the number of roots. This basically describes Boutroux' algorithm. It first constructs the hexahedron by computing the corners of the codomain, then randomly cast a ray from the origin, and found the parity of the number of intersections. However, under floating point calculation, constructing of the corners may introduce numerical rounding errors. Thus, Boutroux employs complicated arithmetic expansion to represent the corners. And they also miss important degenerated cases, making the algorithm inefficient and incorrect. Therefore, we propose our method. We employ a numerical shifting method to exactly represent the corners using floating point numbers, and handle all the degenerated cases, making our algorithm an efficient and exact root parity counter. First, let me introduce the numerical shifting strategy. We found that the corners Vi can be obtained by subtraction operations between mesh vertices. And it's a subtraction that causes the floating point rounding errors. According to Sternberg's condition, 2 floating point numbers a minus b has no rounding error if a over b is between 1/2 and 2. And our shifting strategy is to find the shifting vector E. After shifting, the vertices satisfy Sternberg's condition. Let's explain it with an illustration in 1D. First, we have a simulation scene whose bounding box is between xmin and xmax. And currently Sternberg's condition is not satisfied. Thus, there are rounding errors when constructing the vertices of the CCD codomains. Then we calculate a shifting distance E and shift the whole scene to a position where all the vertices of the CCD domains or codomains satisfy the Sternberg's condition. It requires to change the input of the simulators, and it will perturb the meshes a little bit, like here. The addition will reduce the input precision, but there will be no rounding error when constructing the bilinear surfaces of the CCD codomains using floating point numbers. After casting a ray from the origin, we need to count the parity of the number of intersections between the ray and the bilinear surfaces. Burchell et al. Have already introduced how to count intersection parity for a ray and a non-degenerated bilinear patch. The bilinear surfaces are degenerated when the four vertices are coplanar or collinear. For these cases, Burchell's method will fail. Then the problem will be how to find all degenerated cases and how to count the intersection parity. We propose a simple method to enumerate all the degenerate cases of a bilinear patch. We first enumerate the four vertices from 1 to 4. Then we can find the point P which is not coplanar with a flat patch. We can construct 4 tetrahedrons by connecting P with 3 of the 4 vertices. By calculating the orientations of the point against the 3 vertices of each tetrahedron, we can enumerate all the possible degenerate cases of a linear patch, which are shown here. This figure contains all the possible degenerate cases of a bilinear patch. The horizontal and vertical axes display the orientations of the 4 tetrahedrons. To count the intersection parity between a ray and a bilinear patch, we can simply use an XOR detector. For example, the ray intersects the blue triangle, and the ray intersects the red triangle. By using the XOR operator, we can know that the intersection parity is even. We use a large-scale dataset for CCD to test our algorithm. The dataset contains over 60 million queries, and we shift the queries. We recalculate the ground truth, and we record the number of routes. We have already released the new dataset. Since our shifting algorithm will reduce the input precision, we use the dataset to test the shifting error. The results show that the maximum shifting error is around 10 to the minus 15, which is close to machine epsilon. We also compare our method with 8 state-of-the-art algorithms. The tables on the top and bottom are vertex triangle CCD queries and edge-edge queries separately. The comparison results show that our method is efficient, more stable in runtime compared with IRF, DSC, and tight inclusion. Our method generates no false positives, although it will miss collisions when there are 2 routes, but we only found 7 cases in the simulation dataset, which are really rare. We integrate our algorithm into simulators. The results show that our method works well and enables robust simulation. And it works well even for challenging things like twisting clause. There are several limitations exist in our method. First, our method returns Boolean values indicating if collision happens, but it doesn't directly give the time of impact, although this can be done by a simple bisection process. We can bisect the time interval to have a more and more accurate estimation of when collision happens. Our shifting method requires to reduce the input precision, but the difference is minor and it doesn't change the simulation in a noticeable way. The third limitation is that our method gives the root parity but not the exact root finding result. But the cases are really rare. By shrinking time steps, the number of double roots can be reduced. And as long as the mesh is closed, only the root parity is enough for robust simulation. In conclusion, we propose an efficient and exact root parity counter. Enables robust simulation for closed triangle meshes. We have released the code to foster adoption of our technique. Thank you for coming to our talk. Any questions?